Okay, good evening everyone. I'm Shivani Dhok and I welcome you all for the week 3 tutorial session for the course of simulation of communication systems using MATLAB. So like every week, this week's tutorial will be divided in two parts. The first part will be recap of week 3 content, followed by the questions which are related to week 3 content. So let me start with recap of week 3 content. So in week 3, we started with signals and so if we look at signals mathematically, a signal is a function with a dependent variable which varies with an independent variable. This can be of continuous time, discrete time. This can also be with continuous amplitude and discrete amplitude. Let's not get into that right now. And of course, computer systems can't handle continuous time and continuous amplitude both simultaneously. So we'll go with discrete time signals, and it is quantized based on whatever precision we are using in MATLAB. However, we have discrete time, and in order to get discrete time signals, what we need to do is we need to sample the signal, and this sampling has to be done with the help by some sampling frequency, and the Nyquist sampling theorem gives a condition on the sampling frequency that the sampling frequency fs should be at least equal to 2 times fm for a band limited signal. So this thing is for a band limited signal. Where this fs is sampling frequency and this fm is maximum frequency in the signal. After that, we looked at linear convolution and what is the significance of this linear convolution. Let me add a page. Yeah. So what is the significance of linear convolution? If we have an LTI system with impulse response, let's say h of n, then for an input x of n, y of n, that is output, the output y of n is given by the linear convolution of x of n with the impulse response h of n. And this can be written as summation k running from minus infinity to infinity x of k h of n minus k, or it can also be written as summation k running from minus infinity to infinity x of n minus k into h of k. Both will give me same answers. And this is linear convolution, and then we looked at different ways of implementing this linear convolution. So we saw this like if we implement this formula directly in MATLAB, then it is direct method, and we saw that it requires a lot of operations. Like at every step, for every value of n, we need lot of operations or flops to be done. Another thing that we looked at was using FFT. So this FFT is frequency domain operation. So it is a faster way of implementing discrete Fourier transform. And what it says is, if I have a signal x of n and its DFT, or let's say for now FFT is x1 of k. If I have x2 of n, it's FFT, endpoint FFT is x2 of k. And if I circularly convolve, then that will give me multiplication in frequency domain. Now what we need to do is we need to select this n in such a way. So what we have right now is circular convolution in time gives FFT in multiplication in frequency or in FFT. But what we want is linear convolution. So for that we choose n such that circular convolution is equal to linear convolution. Okay. Now if I linearly convolve, so if x1 has length L and if x2 has length n, then linear convolution of these two, let's say m, linear convolution will lead to a signal of length L plus m minus 1. So what we do is we set n equal to, so if we have n equal to L plus m minus 1, we'll get linear convolution equal to circular convolution. I won't go into details of this, how this is happening, because this is a part of signals and systems or DSP course. So, but you can find all of these details and derivations for this in those kind of courses and the corresponding books. So therefore, if we do endpoint FFT, then we can get this linear convolution done through FFT. So what we'll have to do is we'll first have to take FFT of both the signals, endpoint FFT, then we need to multiply them, and then take inverse FFT to get the linear convolution. Another two ways which were memory efficient were overlap and add and overlap and save methods. After that, we jumped to the concepts of probability. So these probability concepts are quite important considering communication systems, because the source has to transmit something to the user, and that communication is or the communication makes sense only when the receiver doesn't know what the sender or what the transmitter wants to communicate communicate with us, because if that is known, then there is no communication happening. So there is always some sort of uncertainty at the receiver end, like what exact thing has been transmitted by the transmitter, and it has to do decoding and multiple things. So there is some sort of randomness coming into picture. at the source side, and there is some noise getting added, then the channel conditions also change. So there are multiple things that correspond to randomness, and therefore understanding the concept of probability becomes important when we are going for simulation of communication systems and also other things. So then we started with very basic concepts of probability. So we all know that what is a random experiment. We know that an experiment which gives uh, a random output or outcome at every execution of that or every trial of that element, that outcome comes from a pre-specified set which is known as sample space. So the sample space is a set, or let's say collection, of all possible outcomes. So when a trial of that random experiment is done, one outcome from this sample space will come. However, before running that experiment, we can't tell, or we don't know what outcome will be coming, and that is the randomness that comes up. After that, there is a concept what is known as event space. So this event space is a collection of all all the subset of sample space, and in this your null set should be in this so let's say this event space is denoted by script f, should be in your script f, your sample space should be in your script f. Then if some subset of this sample space A is in f, then a complement is also in f. So this event space is basically collection of all possible events. So if A is an event, then A not occurring should also be an event. Similarly, if I have A1, A2 and so on as events, then its union should also be an event. So this, in simple words, this is collection of events and these satisfy certain properties. After that, we have another important concept, that is probability measure. So this probability measure will assign, it is a function from your event space, and that will take value only between 0 and 1. So what we have is the probability of our null set is 0, then probability of your sample space is 1, and if I have probability of A1 union, A2 union and so on, and all of these are disjoint, then this will be equal to probability of A1 plus probability of A2 plus and so on. Another thing that we had seen was inclusion exclusion principle, that is probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Then we looked at what is known as mutually exclusive events. So it says that if one event has occurred, there is no possibility that another will occur. So two events A and B are mutually exclusive if probability of A intersection B, that is both occurring at the same time, is 0. Then we have another concept, that is conditional probability. So let's say we have an event B. So we have an event B such that probability of B is greater than 0, then probability of A given B is known as the conditional probability of event A. given the event B, and it is defined as probability of A intersection B divided by probability of B. Therefore, this thing here is an important thing because of something like this. So this is known as conditional probability. And then we have another important concepts, that is independent events. So two events A and B are independent if probability of A intersection B is equal to probability of A into probability of B, and this thing is equivalent to saying probability of A given B is equal to probability of A. And why is it so? This particular thing here is equal to probability of A intersection B upon probability of B, which will be equal to probability of A into probability of B divided by probability of B. This gets cancelled, which gives me only probability of A. So therefore, these two statements are equivalent. If this is happening, then this will happen. And if this is happening, then this will happen, which means that both of these statements can be taken as the definition for two independent events. Next, we have another concept, that is law of total probability. So what it says is, if B1, B2, B3 and so on partition the sample space, what do you mean by partition? That is AI intersection AJ, sorry, this BI intersection BJ is phi for all I not equal to j, and union of these events is my sample space. Then we can write probability of A as summation n running from 1 to infinity probability of A given Bn into probability of Bn. This thing is known as law of total probability. And then we have this thing which is known as the Bayes theorem. So this Bayes theorem is like this. So we have probability of Bi given A as probability of A given Bi into probability of Bi divided by probability of A, and then we can substitute this definition what we have obtained for probability of Bi as something probability of A. So we get probability of A given Bi into probability of Bi divided by summation n running from 1 to probability of A given Bn into probability of B. So this thing here is known as Bayes theorem. After that, we looked at what is known as the random variables. So random variables by definition are functions x that map elements of omega to real line. So this is my sample space, and this is real line, and this is not a random function, it is a deterministic function. That is, if I know what the outcome I am talking about from my sample space, then I know to what value in real line it will map to. Then these random variables can be continuous, discrete. So this discrete value, okay, Okay, so these will be of two types. We'll see these types one by one. And for all types of random variables, we are able to define a function which is known as cumulative distribution function. So this is the fundamental function for any sort of random variable. So what it says is this CDF, let's say we write it as fx of x for a random variable capital X, is probability that x is less than or equal to small x. And this CDF has certain properties. So first property is fx of minus infinity is 0. Second property is fx of infinity is 1. Then we have it is right continuous. And then we have if x1 less than or equal to x2, then fx of x1 will be less than or equal to fx of x2. That is monotonicity. So this is the fourth property, this is third property. So these are four fundamental properties or defining properties of cumulative distribution function. So any function that satisfies these four properties correspond to CDF of some random variable. Then we have types of random variables, that is discrete. So these discrete random variables take value on a countable set and for these discrete values we have this probability mass function which we can write as px of x equal to probability that x takes value x. And then we have continuous random variables. So for continuous random variables we can write the CDF fx of x as integral minus infinity to x fx of x dx, where this fx of x here, small fx of x here, is known as the probability density function, and we can find this as the differentiation or derivative of the CDF. Okay, so this is continuous random variable and its corresponding PDF, and how we can find the CDF using the PDF, that is probability density function. And after that we looked at some more things which are related to random variables. So the first one was expectation. So for a random variable, or let's say for a continuous random variable, so for continuous random variable, expectation of x we denote it by like this, is integral minus infinity to infinity x into PDF dx. And for discrete random variable, expectation of x is equal to summation x into minus infinity to infinity x into PMF, that is px of x. Then we have another concept which is known as variance. So this variance is given by, or let's denote it by variance of x, which is equal to expectation of x minus its mean whole square. Then in similar way we have mth moment. So this mth moment is simply expectation of x to the power m. There is another thing which is known as mth central moment. So it says that mth central moment is defined by expectation of x minus, you center it by removing the mean and then take its mth power, and this is known as mth central moment. After that, okay, another thing to note here is this is equal to variance for m equal to 2. And at then we looked at what are the functions of random variables. So let's say x is a random variable. Then for nice functions, g of x is also a random variable. And we need to perform transformation of random variables. To get its distribution. And at the end, we looked at the clinical trials. So for clinical trials, we saw how we go for, or how we find the efficiency. So for that, what we said is let I be the set of people, or be the set of infected people, and re be the set of vaccinated people. Then efficiency of this particular vaccine is given by probability that a person is infected given it is not vaccinated minus probability that it is the people are infected given they are vaccinated upon probability that they are infected given they are not vaccinated. And then we looked at how to find out these probabilities based on the number of people, and we looked at the formulas and how to use Bayes theorem in this. So this was just an example to show that probability is an important concept and can be used in multiple areas. So that's all about the content of this particular week. If you have any questions, then please let me know. Otherwise, I'll move on to the tutorial questions that I have planned to cover today. Okay, if there are no questions, then I'll move on to the tutorial questions for today. So, yeah, if you have any question, then please unmute yourself. Oh, okay. Okay, thanks. Thanks. Okay. So let's start with the first question. So again, first 8 questions of this assignment. Okay, okay. So the first 8 questions of this assignment are from last year's sorry, first 8 questions of this tutorial are from the last year's assignment. So hopefully this year's questions will also be similar. So let's see how things go. So the first question here is the FFT operation is computationally efficient to compute Fourier series, continuous time Fourier transform, discrete time Fourier transform, and discrete Fourier transform. In principle, FFT is faster way to implement the discrete Fourier transform. So this Fourier series can have discrete time Fourier series and continuous time Fourier series. Then you have, these are for periodic signals. Then we have continuous time Fourier transform for aperiodic continuous time signals. Then we have discrete time Fourier transform for aperiodic discrete time signals. And then we have this thing known as discrete Fourier transform. So this discrete Fourier transform for a signal xk, so let's say n point DFT for the signal x for x of n is x of k, which is equal to summation n running from 0 to n minus 1 x of n into e power minus j 2 pi k n by n. And this is the discrete Fourier transform, and faster way to implement this is FFT, and it takes order of log n computational complexity, and which is the best which we can achieve. So the faster way to implement discrete Fourier transform is FFT. If you have any questions, then you can unmute yourself and ask, else I'll move on to the next question. Okay, so the next question is, which of the following requires the least number of operations or least number of computations? So the direct method requires a lot of operations, so obviously this is very inefficient. This FFT based requires order of n log n operations, and this is less than direct. Then we have overlap and add and overlap and save method. So what these two do is they break the signals into small parts, perform FFT or perform convolution using FFT for each chunk, and then do add or save operation, which means that these are doing additional operations than simple FFT based convolution. Which means FFT based computation for convolution will need the least number of operations or computations. Any questions? Okay. So let's move on to the next question. So this question is, the event space of a discrete sample space is. So first option is sample space itself. Second option is power set of sample space. So what do you mean by power set? So power set is collection of all possible subsets. So let's say power set of a set A, subsets of set A. Okay. And the last one is a null set, and fourth one is cannot be defined. So if I have a discrete sample space, obviously in the null set, only the null set cannot be an event space. You need some other outcomes to be there. So of course the third option is not correct. Similarly, cannot be defined is also not correct. The first thing is sample space itself. So if I have a sample space which is omega equal to omega 1, omega 2 and so on like that, if I have these, then two outcomes occurring together can also be an event. Okay, so what happens is this union, so for in an event space, union and intersection should also be an event. And this particular thing is not happening when we consider only the sample space. And therefore, if we consider, so again, this is not the correct option. So if we consider power set of A, so it is having all possible collection of all possible subsets of your sample space, because it is a power set. So now if I consider two sets from this power set A and B, and if I take its union, that will be in my power set. Similarly, if I take A intersection B, that will also be in my power set. Therefore, this power set also a null set is subset is an element of power set because it's subset of your sample space, and the entire sample space also is a subset of itself, and therefore that will also be in my power set, and therefore it satisfies all the properties, and hence this power set of sample space is an example of event space for a discrete sample space. Is it clear? Any questions here? Okay, if there are no questions, then let me move on to the next question. So the next question is again simple. It says that the events E and F are mutually exclusive if first option is probability of E intersection F is equal to probability of E into probability of F. So this is the condition for independence. Let me write it below. One is a condition for independence. Therefore, this is not a correct option. Then probability of A intersection F is equal to 0. So this is basically the definition of mutually exclusive events. So this is the correct answer. And then we have two options which take into account probability of A union F. So let's try to see what happens is probability of A union F is given by probability of E plus probability of B minus probability of E intersection, sorry, not B, F, E intersection F. Now this E intersection F is equal to 0 because they are mutually exclusive, and therefore this reduces to probability of E plus probability of F, which means that this option is wrong, as the probability of union equal to 0 is wrong. However, probability of E union B equal to probability of E plus probability, oh sorry, this is F. Probability of F is correct option, and therefore this is also the right option. So this was a multiple answer correct question. Most probably in your assignments it will be clearly mentioned, or instead of radio buttons you will have a checkbox, a square checkbox. If you have those kind of things coming there, then it will be a multiple answer question. It will be it can be seen in some way or the other. Instead of radio buttons, if you have something else, then it might be a multiple answer correct question. So be careful. Any questions in this part? First condition. Okay. So this probability of A intersection B, two events E and F are independent if probability of sorry E intersection F is equal to probability of E into probability of F. Instead of writing condition, I should write it is definition. And these doesn't say anything about mutually exclusiveness. So if the probability of intersection probably productifies into the individual probabilities, that is probability of intersection F, if it is equal to probability of E into probability of F, then it simply means that these two events E and F are independent. It says that E and F are independent. It has nothing to do regarding mutually exclusive events. The definition for mutually exclusive events is probability of A intersection F, E intersection F is equal to 0, which means that occurrence of if E occurs, F cannot occur, and if F occurs, E cannot occur. E and F can never occur jointly. That's why it is mutually exclusive event. I hope it's clear now. Okay, yeah. So if it is clear and there are no further doubts, I'll move on to the next question. Excuse me. Okay. So what is given to us is, so the question says the mean squared value of a random variable having mean mu and variance sigma square is. So what we need to find is mean squared value of a random variable. So now let's say that x is a random variable and what is given to us is its mean equal to expectation of x is mu and variance, which is expectation of x minus mu whole square, is equal to sigma square. And what we need to do is we want to find mean squared value, which is simply expectation of x square. So if we observe carefully, intuitively, there is some relation between mean, variance and mean square. So what we can do is we can have, let's start with variance. So we have sigma square is equal to expectation of x minus mu square. This is equal to expectation of x square minus 2x mu plus mu square. Then we can apply linearity property of expectation. That is, if expectation of x plus y, or to be very precise, alpha x plus beta y, that will be equal to alpha times expectation of x plus beta times expectation of y. So we can use that, and therefore we'll have expectation of x square minus 2 mu. These two are constants. I can take it outside. Expectation of x plus mu square. Mu is constant. Then we have expectation of x square minus expectation of x is mu. So this will be 2 mu square plus mu square. This is equal to expectation of x square minus mu square. Therefore, we have expectation of x square equal to sigma square plus mu square. So this mean square which is also known as the second moment is equal to variance plus mean whole square. Okay, so therefore this, if we look at the options given to us, so the correct option that we have is mu square plus sigma square. Any questions? Okay, there are no questions, then let's move on to the next question. Okay, so the next question says the cumulative distribution function of a random variable is, first option is this continuous, second option it is right continuous, third option it is left continuous, and last option it is differentiable. So by definition, or by the properties of cumulative distribution function, it is right continuous. So this is, so let me just write the defining properties. So a CDF, so this cumulative distribution function is CDF of a random variable x, that is, let's say fx of x, has 4 defining properties. The first property is fx of minus infinity is 0. Second property is fx of infinity is 1. Third property is it is right continuous. And fourth property is if x1 is less than x2, then fx of x1 is less than or equal to fx of x2. This is known as monotonicity. But what do we mean by right continuity? So right continuity means you have a value here, let's say x. So you approach from right side like this. Then if we approach, so the right limit, if it is continuous, then we say that it is right continuous. So it simply means that limit y tending to x plus fx of x, fx of y is equal to fx of x. Okay, this is also known as y approaches to x. This is also another notation to write the same thing. Okay, so if for an example, if we see, let's say I have a random variable which is x, and okay, so this is, let's say, a Bernoulli random variable, So Px of x is equal, so x takes value within 0 and 1. So x is equal to 0 with probability 1 minus p, and it is equal to 1 with probability p. So now if I have px of x, sorry, CDF fx of x, which is probability that x is less than or equal to x. So this will be equal to, so it's like this. I have this line here. This is my 0, this is my 1. So if my x lies here and 0 is not included, then my CDF will be equal to 0, because I am not taking into consideration anything. There is no event occurring. So therefore this will be equal to 0 if x is less than 0. So it will be, let me just draw it properly. So in this region, it will be equal to 0. Note that it is not 0 at 0. Now, if I am in this region, that is including 0, if I am here in this region and excluding 1. So if I am between 0 less than or equal to x less than 1, then in all this region, your x equal to 0 will be included, and x equal to 0 has probability 1 minus p. So this will be equal to 1 minus p. So it will be like this. At 0 also, I'll have a probability of 1, 1 minus p, and this will continue till 1, and here for 1 it won't be equal to 1, and then for x greater than or equal to 1, this will be equal to 1. That is because I'm considering all the possible outcomes, that is all the possible values of x, that is 0 and 1. So then at 1 it will be 1 and it will continue. So now what we observe here is this particular jump is probability that x equal to 0, and this particular jump is equal to probability that x equal to 1. Okay. So now what we observe here is, if we approach this 0 from right hand side, that is limit x tending to 0 plus, will have the limit as 1 minus p, which is equal to your fx of x. However, if I approach from left like this, then there is a discontinuity here. Similarly, there is a discontinuity if I approach like this, because for left limit, the value will be 1 minus p. However, for right limit and that particular value, your value of the function comes out to be equal to 1. So therefore, this CDFs are right continuous, they are not left continuous. They may or may not be left continuous. There are conditions when the CDF is continuous completely, but they have to be right continuous. So therefore, this right continuity is the defining property of CDFs, and that's why this is the correct option. Any questions? Okay, if there are no questions, then let's move on to the next question. Okay. So what we have here is, the question says that the probability density function of a random variable is A positive, B non-negative, 3 negative and the non-negative. Okay. So this f of x, so for a continuous random variable, let me write it in this way. For a continuous random variable, your CDF can be written as integral minus infinity to x fx of t dt. Okay. And the CDF, by the monotonicity property, this is non-decreasing. What does this non-decreasing means? It can increase or remain constant but cannot decrease. So therefore this is always a non-decreasing function. And we have seen that this fx of x, this thing here, fx of x is the PDF, and this fx of x is basically the slope of this CDF. Now the CDF is a non-decreasing function. We have seen that this is a non-decreasing function, which means that this will be greater than 0 if it is monotonically increasing function, and if it remains constant, it can be equal to 0. So if the CDF remains constant over a particular interval, then at that point my PDF will be equal to 0. So what it means is my fx of x is greater than or equal to 0, which means that it cannot be negative, or it is non-negative. So the correct option is non-negative. It's not just positive, it can be non-negative also, because it can take the value 0 also. Any questions here? Okay, if there are no questions, then let me move on to the next question. Okay, so this is the next question, and it says that what it asks us to do is, let's read the question first. The expected value of a binary random variable. So it is a binary random variable which takes value as 1 with probability p. It is equal to 2 with probability 1 minus p. So what is given to us is a random variable x, which is a binary random variable. It takes only two values, that is 1 and 2. And it takes the value 1 with probability p, and it takes the value 2 with probability 1 minus p. So what it means is the PMF px of x takes two values, that is 1, sorry, yeah, it takes two values, that is p if x equal to 1. It is 1 minus p if x equal to. And what we need to find is, we need to find expectation of x. Okay, so for a discrete random variable, look at this. This takes value on, this takes only two values. It takes countable values, which means that this x is a discrete random variable. This is a discrete random variable. And therefore, for a discrete random variable, okay, so for a discrete random variable, what we have is expectation of x is equal to summation over x into px of x. So here this x takes two values, that is x belongs to 1 and 2. So therefore I can write this as 1 into px of 1 plus 2 into px of 2. This is equal to 1 into what is px of 1? We have found out, or it is given to us as p, plus 2 into what we have is, for x equal to 2, the value of PMF is 1 minus p. 2 into 1 minus p. So this is equal to p plus 2 minus 2p, which comes out to be equal to 2 minus p. So therefore expectation of x is equal to 2 minus p. Similarly, let's do one more step. Since we have a lot of time, just suppose we need to find variance of this x. So we have expectation of x minus expectation of x whole square, and we had seen that this comes out to be equal to the second moment minus the first moment square. So that is equal to expectation of x square minus 2 minus p square. So this we know. So what remains is to find out what this particular thing is. So therefore we can find out expectation of x square as summation x over whatever support we have. Here it is 1 and 2, x square into px of x. So then we have for x equal to 1, px of 1 plus 2 square minus, into px of 1 minus px of 2, that is equal to p plus 4 into 1 minus p, which comes out to be equal to 4 minus 3. So therefore variance of x is equal to 4 minus p minus 2 minus p square, which comes out to be equal to 4 minus p minus 4 minus 4p, this is 3 plus p square. So this 4 gets cancelled. Then we have minus 3p plus 4p minus p square. This comes out to be equal to p minus p square, which I can write as p into 1 minus p. Okay. So this is the variance, and in general, if you want to find expectation of any function of x, and that we can write as x over its support g of x into px of x. This is for discrete random variable, and expectation of g of x is equal to summation x, sorry, integral x g of x into its PDF dx for continuous random variable. Okay, so these are some standard things that we can do. If you have any questions, then let me know. Otherwise, I'll move on to the next question. Okay, if there are no questions, then let's go to the next question. So this last two questions are not in assignments, but I feel that these are some good and important questions that we should look at. That will give us some insights also, which will help us in the upcoming things. So the first, okay, the question says is, for the following random variables, the CDF is given and we need to find the respective probability density functions. So basically what we are given is the CDF of continuous random variables. And then we need to figure out what is the PDF of these things. So let's start with the first one. So the first one that is given to us is fx of x is 1 minus e power minus lambda x for x greater than or equal to 0 and for lambda greater than 0. One thing we need to note here is this particular random variable is known as exponential random variable. And we shall encounter this random variable in coming lectures. Okay, so this we have, and we know that this is a continuous random variable, and therefore fx of x, or PDF little fx of x, is just a minute. Okay, fx of x is d dx of fx of x, which is d dx only for positive values of x. We have 1 minus e power minus lambda x, which is equal to lambda into e power minus lambda x for x greater than or equal to 0. So therefore the PDF of an exponential random variable, therefore PDF of an exponential random variable is fx of x is equal to lambda e power minus lambda x for x greater than or equal to 0. So how does this look? We have this fx of x and x. We have fx of x as lambda e power minus lambda x for x greater than or equal to 0. So at x equal to, before x equal to 0, it is 0. At x equal to 0, it takes value as lambda, and then we have an exponential decay. So this is known as the exponential random variable, and its CDF fx of x, which is 1 minus e power minus lambda x for x greater than or equal to 0. So till this point it is, so again this is like this, and at x equal to 0 it is 0. So and then it increases like this and then saturates, slowly starts to saturating. So basically this is the value of 1, and it slowly starts attaining 1, and this is simply the CDF. So this particular plot is for PDF and this particular plot is for CDF. So this is for exponential random variable. Now let us take just a minute, I'll add slides. So that was all for the first one. Then let's move. If you have any questions in the first part, just let me know. Okay, if there are no questions, then let me move on to the next part of this. So the next part is fx of x is 1 minus, so capital Fx or CDF is 1 minus e power minus x square by sigma square for x greater than or equal to 0. This is also an important distribution. This is known as Rayleigh distribution or Rayleigh random variable. Okay. Okay. So this is what we are having. Okay. Just a minute. So this is Rayleigh random variable. This is again what we call as the continuous random variable, and therefore we have fx of x as ddx of fx of x, which is equal to ddx of 1 minus e power minus x square by sigma square, and it comes out to be equal to 0 minus e power minus x square by sigma square into minus 2x by sigma square. So this comes out to be equal to 2x by sigma square into e power minus x square by sigma square, and this is for x greater than or equal to 0. Okay. So this particular random variable is Rayleigh random variable. So let me just again summarize in the same fashion what we did. So what we have is the PDF is fx of x is equal to 2x by sigma square into e power minus x square by 2, sorry, x square by sigma square for x greater than or equal to 0. Okay, and if that is the case, how will it look? So anyway, it is 0 before 0. It is 0 before 0. And at 0 also it is 0. Then it will slowly start to increase to a certain point where this linear x term will dominate for low values of x, and after that this exponential decay starts dominating, which makes it go like this. So this is the PDF for Rayleigh distribution. And then we have this CDF. So its CDF was fx of x equal to 1 minus e power minus x square by sigma square for x greater than or equal to 0. So again what we have is so it is 0 here, and before or less than 0 it is 0, at x equal to 0 also it is 0, and then it slowly starts increasing and again it saturates, where it starts to saturate like this. So this is 1, it can't go beyond 1. So this is the Rayleigh distribution. Any questions here? Okay, if there are no questions, then let me move on to the next question, or the next part of the same question. So yeah, so the CDF that is given to us is this one now. Okay, so what we have here is this fx of x. It is 0 for x less than a. It is x minus a by b minus a for a less than or equal to x less than or equal to b. And it is 1 for x greater than. Okay, so now what's happening here is this fx of x, which is d dx of fx, sorry, of fx of x, this comes out to be equal to, for x less than 0, so again I'll have three cases. For x less than a, it is anyway 0. Then for x ranging from a to b, it will be equal to derivative of this quantity here, that is x minus a by b, sorry, this is not b, this is a. Yeah, so this will be, so in this range, that is x minus a by b minus a, the derivative of this particular quantity will be 1 upon b minus a. And for x greater than b, again this fx is a constant, and therefore this will be equal to 0. So now what happens is, this particular random variable takes a constant value over a particular range, and it is uniform in that range, and hence this random variable is known as uniform random variable. So this is uniform random variable. Okay, so again let's do the same thing. So we have a uniform random variable. So then we have its PDF. So its PDF is fx of x equal to 0 for x less than a, 1 upon b minus a for x belonging to a to b, and it is 0 for x greater than or equal to, sorry, x greater than b. So how it looks is something like this. So we have this x, then we have a, we have b, then here it is 0, then it from a to b it uniformly takes value as 1 upon b minus a, and from b, sorry, and then I have it something like this. So this is the uniform density or uniform distribution probability density function. Then we have CDF, in which fx of x is equal, sorry, CDF, capital Fx of x is 0 for x less than a. It is equal to x minus a upon b minus a for x belonging to a to b. It is equal to 1 for x greater than or equal to, sorry, greater than b. Then what we have is, again we have this thing, we have this axis x, we have a, we have b, and then we have another thing that is saturation value of, so this is the value 1. So for x less than a it is 0, for x greater than b it is 1, and if you observe carefully, from a to b it linearly increases from 0 to 1. So if you substitute a here, then it will x equal to a in this, it will give me 0. So at a it will be 0, and if I substitute x equal to b, it will be 1. So at b equal to 1, so in this range it will linearly increase. So this is nothing but CDF, is fx of x, and this is nothing but PDF, that is fx of x for uniform random variable. Any questions? Okay, if there are no questions, then let me move on to the last question. Just a minute. Anyways, yeah. Let me move on to the last question that I have planned to cover today. So this is an interesting question and gives good insights. So I just wanted to take this up. So this has two subparts. So let's focus on the first subpart first. So what it says is, consider a discrete random variable with PMF Px of with PMF given by this, and we need to find the probability that x is greater than k plus n, condition that x is greater than k. So this thing is for all k and n great in natural numbers. That means k and n will only take positive values. Okay, so what's happening is, so for the first part we have probability that x is greater than k plus n, condition on x greater than k. Okay, another thing that I would like to mention initially is this px of k equal to 1 minus p k to the power k minus 1 into p for k greater than or equal to 1, or let's say k belonging to the set of natural numbers. This is a geometric random variable or geometric distribution. Okay. So what we need to find out is probability that x is greater than k plus n conditioned on x greater than k. This we can write as probability that x is greater than k plus n intersection x is greater than k divided by probability that x is greater than k. So what's happening here is you have this k and then you have this n plus k. Okay, so this x greater than k is this particular part, and this n plus k, x greater than n plus k is this part. So if I take intersection, the numerator will simply reduce it to x greater than k plus n divided by probability of x greater than k. And this thing we can write as 1 minus fx of k plus n upon, or let me take it to the next page. So what we are having is probability that x greater than k plus n conditioned on x greater than k is equal to probability that x is greater than k plus n upon probability that x is greater than k. And this I can write as 1 minus probability that x is less than or equal to k plus n, or okay, let's keep it like this only. For now we can write it in terms of CDF, but we'll just keep it like this only. Now what we need to find out is these two quantities. So let's just find, this is also another natural number k plus n. So let's say we figure out this thing, x greater than or equal to some value m, where m belongs to natural numbers, not equal to, greater than. So this we can write as L ranging from m plus 1. So it is greater than m. It is not equal to m, so we can't start our lower limit from m. So L ranging from m plus 1 to infinity px of L. Okay, and this we can write as summation L ranging from m plus 1 to infinity p into 1 minus p to the power L minus 1. So this p is constant, and then we have this sum L equal to m plus 1 to infinity 1 minus p to the power L minus 1. So this particular thing here is infinite geometric progression with PMF, with first term as 1 minus p to the power m and common ratio as 1 minus p, which is less than 1. Okay, so this thing here is now p into 1 minus p to the power m divided by 1 minus the common ratio. So this thing in the denominator, this 1 gets cancelled and what remains is p. So this p gets cancelled with this p, and therefore what is left with us is probability that x is greater than m is equal to 1 minus p to the power m. So this is what we are having here. Now let's get back to the actual question that we had. So let's look at this equation again. So let me just number it as 2. Okay. So from equation, or substituting this, in 1 we get probability that x is greater than k plus n upon probability that x is greater than m, or let me write it properly, x greater than k plus n, given x is greater than k, which we obtained as probability that x is greater than k plus n upon probability that x is greater than k. This will be 1 minus, so the numerator will be here my m is equal to k plus n upon 1 minus probability of k. Okay. So now what we obtain here is this gets cancelled and we have 1 minus p to the power n. And if we compare it with equation 2, this is nothing but probability that x is greater than n. So in principle what we are obtaining is probability that x is greater than k plus n given x greater than k is simply equal to probability that x is greater than n. So what it means is, if I have reached, or if my x is already greater than k, I have reached certain point of random variable, and after that if I want to check whether the random variable has a value greater than n, it has nothing to do with whatever has been done or whatever has been observed earlier, which means that there is some sense of memorylessness. Okay, so this geometric random variable shows this particular kind of property, which is an interesting thing to look at. Now let us, any questions in this particular part? If you have any questions, then let me know. Okay, if there are no questions, then let me move to next part of this question. So let's move to the second part of this question now. So the second part says that consider a continuous random variable with CDF fx equal to 1 minus e power minus lambda x for x greater than or equal to 0. We have seen this CDF earlier. This is for exponential random variable. In last question only we have seen this. This is exponential random variable. And we need to repeat the same exercise. That is, we need to find this conditional probability that x greater than s plus t is given x greater than t for all s and t greater than or equal to 0. So what we so what we need to find out is probability that x is greater than s plus t conditioned on x greater than t. This is equal to probability that x is greater than, write it up properly, x greater than s plus t intersection x greater than t divided by probability that x is greater than t. So again same thing, what is happening is my s and t both are positive. So my s is here and my t here, s plus t is here. So this is the region for s, sorry, I need to do ulta. T is here and s plus t is here. So this is the region where my s is greater than, my x is greater than t, and this is the region for my x is greater than s plus t. So if I take intersection of these two regions, what it will give me is the same region where x is greater than s plus t. So what we have now is, this is equal to probability that x is greater than s plus t divided by probability that x is greater than t. Now this thing we'll have to write in terms of the CDFs. So what we have now is probability that x greater than s plus t conditioned on x greater than t, and this we have seen to be equal to probability that x is greater than s plus t upon probability that x is greater than t. The numerator I can write as 1 minus probability that x is less than or equal to s plus t, and denominator I can write as probability that x is less than or equal to t. So this particular quantity here, probability x less than or equal to s plus t, is simply CDF evaluated at s plus t. Similarly, in denominator, this particular quantity is simply CDF evaluated at x equal to t. Okay. So now what we have here is 1 minus fx of s plus t upon 1 minus fx of. Now what is the CDF given to us? We are given fx of x equal to 1 minus e power minus lambda x for x greater than or equal to 0. Okay, so therefore what we get is probability that x greater than s plus t given x greater than t, which is equal to 1 minus fx of s plus t upon 1 minus fx of t. This comes out to be equal to 1 minus e power minus lambda into s plus t divided by 1 minus e power minus lambda t. So this one gets cancelled, this also gets cancelled, and what we are left with is e power minus lambda s plus t divided by e power minus lambda t, which I can write as e power minus lambda s into e power minus lambda t upon e power minus lambda t. This gets cancelled, and what we are left with is simply e power minus lambda s. So again, what we have obtained here is something nice. So therefore, probability that x is greater than s plus t given x is greater than t comes out to be equal to e power minus lambda s, which I can write as 1 minus e power minus lambda s, which is equal to 1 minus fx of s, which we can again write as probability that x is greater than s. So very similar structure we have obtained, or the same structure we have obtained as in the first part. In first part also we have seen that we get something like this, and similarly in second part also we are getting this particular thing here. So again, this exponential random variable is also showing some sort of memorylessness. So this is also showing some sort of memorylessness. So what about this is, so if a random variable shows these kind of results, then such a random variable is known as a memoryless random variable or memoryless distribution. So if a random variable x satisfies, or let's say like this, a random variable x is memoryless if it satisfies the following property. Okay, so what is the property? Probability that x greater than s plus t conditioned x greater than t. If this is equal to probability that x is greater than s, then such a random variable is known as memoryless random variable, memoryless distribution. Now another interesting thing is Geometric random variable or geometric distribution is the only memoryless discrete random variable, and exponential random variable is the only memoryless continuous random variable. So these are some interesting properties of these two distributions which can be used to solve many questions which are related to exponential random variables or geometric random variables. If you have any questions in this part, please feel free to ask. If you have any questions in any part of today's tutorial, you can ask. If you have no further questions, that is all I wanted to cover today. You're free to leave the meeting, and thank you for attending today's session.